Hello, my name is Stephen Ray from Bristol University, and I'm going to present my PhD, Novel Self-Healing Systems, and focus specifically on expanding healing agents. So a quick outline of the presentation: I'm going to introduce the problems of composites and limitations of current self-healing systems, and then talk about the development and testing of an expanding healing agent and some initial experiments where we employed these healing agents to heal damaged areas. So composite structures are becoming more and more prominent in structures, and this is due to the superior properties over metal components such as lightweight, stiffness and fatigue performance. But there's a reluctance to trust composites in design due to the formation of small cracks in the structures, and this leads to an over-design and therefore thicker components than we need, which are obviously much heavier. This lack of trust in composites comes from the fact that composites are almost completely elastic to failure. There's no plastic deformation mechanism. So in an impact event, often the upper plies will recover elastically, whereas in the inner plies there will be delamination, crack formation and debonding between the fibres in the matrix. As you can see from this CT scan here of an impact on a composite plate, there can be a significant damage volume internally. So the current approaches that we're investigating at Bristol for self-healing take two forms: microcapsule systems, whereby microcapsule spheres are dispersed in the matrix, and when an impact event occurs, they're ruptured, releasing the unreacted monomer, and this comes into contact with a catalyst in the matrix, thus curing. Or we can have a two-component microcapsule system where the two components mix and then heal. The other system we look at is a vascular system, which has a network of channels where we can pump the healing resin into the damaged area, thus healing it. The other area of research we perform at Bristol is crack redirection, so we can force the cracks to drive them towards an area of self-healing to ensure that they are healed. But these systems come with their own limitations, namely storage life, cure kinetics, and achieving stoichiometric mixing. And importantly, they'll have a limited volume of healing, especially with microcapsules. And also we have a problem with, after the impact event and the delivery agent has been, the healing agent has been delivered, we're left with the voidage of empty microcapsules or vascules. These problems can be overcome by using a healing agent that's capable of a volume expansion. Not only will it allow us to heal a greater damage volume, but will also allow us to heal a greater proportion of that damage. And of course, it also eliminates the problem with voidage left behind with the delivery system. But developing such a new system requires an entirely new approach to the chemistry required, and we have to consider each of these factors on the slide here. The first system we've been looking at is an epoxy resin-based system. Two parts. Part A uses bisphenol A and bisphenol F, and Part B is various amine hardeners, and this comes in two forms. We can have a low density foam produced that gives a higher expansion, about 300%, or we can have a higher density foam produced with a lower expansion, about 170%. With each of these systems, once the two parts are mixed, expansion will start within 2 minutes and usually be complete after 1 hour. And it takes another 5 to 6 hours to fully cure the healing agent. So to test the mechanical properties of each of these epoxy-based systems, performed flexural testing, and we got the strength and the flexural modulus of these systems as shown here. In expanding a healing agent, we were concerned that in expanding the volume, we would lower the properties. So we thought, how can we mitigate against that? And one of the ideas was to incorporate chopped carbon fibre into the system to try and mitigate against this drop in performance. As you can see from the figures in the slides, we get a significant increase in the material properties by including the carbon fibre in there. So to investigate what was going on when we tested these samples to failure, we've done some SEM analysis of the fracture surfaces and to characterise the foam itself. And each time we saw a regular, consistent cell size, and also it was a closed cell structure, and incorporating the carbon fibre in there had no influence on the morphology. On the fracture surfaces of the fibre reinforced foams, in each case we could find examples of fibres protruding from the surface and also holes which diameter was of the same magnitude as the diameter of the fibres. These images and the increase in performance we've seen, we think we're confident this indicates some kind of fibre pull-out mechanism. The setting system that I've been developing is based on a polyurethane system. Again, two parts. Part A being a polymeric isocyanate, and part B being a blend of polyol, which reacts with the isonate to give you the polymer itself, a blowing agent in there which we can evaporate to increase the expansion, a surfactant which helps bind everything together and keep it stable, and of course a catalyst to get the reaction to occur. As you can see in the video, when the two parts are mixed, rapidly we get an expansion, but usually less than 10 seconds, and quite a significant expansion in that. This system is much more versatile in that we can alter the amount of blowing agent in there and vary the expansion. That being an example of how extreme it can be. So how does this work? Two reactions proceed at the same time. Blow reaction, where the decomposition of carbamic acid which forms in the reaction decomposes, giving off carbon dioxide. This is the main blowing agent that allows the polymer to expand, but also involves heat, and we can use that heat to evaporate a solvent that's mixed in there if we want additional expansion. And at the same time we have the gelation reaction, which is the actual polymerization reaction itself. So to test these, the epoxy system and the polyurethane system, we used it to repair an already failed epoxy block and then compared the stiffnesses after we tested it again. As you can see from the graph, using the epoxy system we get a very close match to the same stiffness as the virgin sample. And again with the polyurethane system, it's a high stiffness recovery, but as expected a bit more elastic due to the viscoelastic nature of the polyurethane. But this could be an advantage in fatigue performance for healed samples. So to summarise the two healing agents, epoxy system, simple two-part chemistry, and we consistently get a high stiffness recovery. We can easily incorporate a reinforcement in there, but it's much higher viscosity and relatively slow to react. With the polyurethane system, it's much more versatile. We can tailor all the properties we want, very fast to expand and cure, but the downside is it's a bit more complex and precise chemistry required. So to actually test these healing agents in a bit more lifelike scenario, we've done some DCB tests. They get the baseline result as shown by the blue line on the graph, and then healed that with one of the expanding healing agents and tested again. As you can see, we've got a very close stiffness match and also takes a much higher load. And in each case, we found there was cohesive failure of the healing agent rather than adhesive failure, which is ideal for self-healing systems. So to this work in the future, we're going to be using each of the healing agents I talked about in DCB testing, analyse the failure modes. We're also going to be using these healing agents to repair sandwich panels, test them, and assess their performance in that scenario. Thanks very much for listening, and thank you to the EPSRC for funding this project and to Axis.